Okay, here we are going to discuss the dual problem. The dual problem is associated with linear programming problem. That is, if you have a basic problem for which you are trying to find a solution using linear programming technique, that is usually referred to as a primal problem. And for every primal problem, there is a corresponding dual problem. That is, we can take the case of a firm that is trying to find out what are the optimal quantities of commodities to be produced so as to maximize its profits. So in that case, its primal problem is profit maximization. Now, for the very same firm, its dual problem would be cost minimization. So, your dual actually depends on the nature of the primal. If the primal problem is maximization, in that case, dual will be minimization problem. Contrary to that, if your primal problem is minimization, then your dual problem would be maximization. Now, let us now try to write this dual and that is primal problems. Let us take this case. Uh, Here we have a that is a primal problem that is being stated where we write that is maximize zx is equal to c1 x1 plus c2 x2 plus up to plus cn xn. Of course, that is the optimization problem that's objective function of the firm, and this happens to be a maximization problem because we are showing it as maximize zx. Now, as usual, this would be subject to a set of linear constraints, isn't it so? Where you have both technical constraints and non-negativity constraints. Here, the linear constraints can be written as a11 x1 plus a12 x2 plus up to plus a1n xn less than or equal to b1. Right. For instance, if the firm is trying to maximize its profits, it's subject to several constraints in the form of land, labor, capital, etc. These are all factors of production. The quantities of that are not unlimited. They are constraints. So let's say that this is your first constraint that is less than or equal to B1. Similarly, you have the second constraint. Maybe your land is a constraint. So you can write A21 x1 plus a22 x2 plus up to plus a2 and xn less than or equal to b2. And here you have numerous constraints. Capital is a constraint. Okay, so many constraints are there. Finally, you have m number of constraints. Okay, that is am1 x1 plus am2 x2 plus up to plus amn xn less than or equal to bm. So these are all your technical constraints which you have written. Okay, these are all your technical constraints. And then apart from that, you also have non-negativity constraints. That is why you write x1, x2 up to xn greater than or equal to 0. These are all your non-negativity constraints. So this is how you write your that is maximization problem, which is your objective function subject to set of constraints. Now, from this primal problem, you can actually arrive at your dual problem. Okay, while you write the dual problem, actually you're constructing that problem from this primal problem, right? What you do is that you write your objective function as minimize. Instead of maximize, it is now minimize. Zy is equal to. Now, all the constraints that is in the right hand side of this linear inequality. Okay, you have mentioned b1, b2 up to bm. All these fall to the right hand side of this linear inequality sign. That becomes a part of your objective function in the dual. Okay, in the dual, which is objective functions minimization. So this b1, b2 up to bm, that becomes a part of the objective function of the dual. So you can write this as b1 y1 plus b2 y2 plus, okay, up to plus b m y m. Okay, that is how you write the minimization problem, right? Then another thing, what is that minimization problem or the dual problem is also subject to a set of linear constraints. Just like that, you have in a primal problem, in the dual problem also you have so many linear constraints, both technical constraints, functional constraints, and non-negativity constraints. Now, how do you write this? That is non-negative. How do you write this technical constraints? Now, for this, just have a look at these coefficients, okay, of these x1, x2 up to xn. Okay, just form a matrix based on that. Let us write a coefficient matrix A. It is a11, a12, isn't it so? up to a1n, right? Okay, and similarly in the second linear constraint, when you take that, the coefficients are a21, a22 up to a2n, and then it goes on like that. Then finally, in the last constraint, you have am1, am2 up to amn. This is how you form a coefficient matrix. Okay, this is the original matrix A based on the primal problem. Now, what you do in dual is that all that you have to do is you have to just take a transpose of this coefficient matrix. This is the original matrix that you construct based on the primal problem. Now, for constructing the dual, what you do is that you just take a transpose of the coefficient matrix A. That is, you just interchange rows into columns and columns into rows. So this becomes, here it becomes A11, right? A21 up to AM1, isn't it so? Then A transpose, it becomes A12, A22 up to, that is AM2. And then you have, it goes on like that, a1n, then a2n up to amn. So this is how you write the transpose of the coefficient matrix that you have seen in the primal problem, that is transposed so as to get a new coefficient matrix in the dual problem. Right, now based on this transpose matrix, you can construct the linear constraints of the dual problem. This can be written as a11y1 plus a21y2 plus up to plus am1ym. That is the constraint that you are constructing based on the transpose of this original primal matrix. Now, here in the primal problem, you are using the inequality sign as less than or equal to. Here in the minimization, then the inequality sign becomes greater than or equal to. And here instead of b1, b2 up to bm, in the objective function of the primal problem, you are using C1, C2, Cn, isn't it? So here you can write C1, right? The constants that you have used in the minimization, sorry, or primal problem, in the maximization problem, that becomes your constraint. Okay, that comes to the right hand side of your inequality. Okay, in the constraint in the case of the minimization problem, right? The next constraint can be written as A12, A12 y1 plus a22 y2 plus up to plus am2 ym, which is greater than or equal to c2, and that goes on like that. And finally you have a1n y1 plus a2n y2 plus up to plus amn ym, that is greater than or equal to, that is you have Cn, right? Okay, that is Cn. So these are the technical constraints of the dual function, right? Apart from that, you also have a non-negativity constraint where y1, y2 up to ym, all these are that is greater than or equal to 0, right? These are the non-negativity constraints. So from this, what you can say is that if you have a primal problem, from that primal problem, you can actually construct a dual problem. The things that you have to notice here is that if the primal problem is maximized, dual problem is minimized. Okay, then in the objective function, you use constants like C1, C2 up to Cn, etc., which means that you have n number of variables. And here, this C1, C2, Cn, etc., which is a part of the objective function of the maximization problem, it becomes the constraint in the minimization problem, which is your dual. Similarly, another thing that you can observe is that in the maximization problem, the inequality sign that that you use this inequality is less than or equal to, but in the corresponding dual minimization, the inequality that you make use of is greater than or equal to. Then another thing that you can observe is that there are m number of constraints and n number of variables in the primal problem, which is maximization problem here. And contrary to that, in the minimization problem, you have n number of constraints and m number of variables. Okay, that's what you've observed in the dual problem, which is minimization in this case. Then we can see that in the maximization problem, that is primal problem here, in the constraints, in the technical constraints, to the right hand side of the linear inequality, you have these terms b1 b2 up to bm. These are the constraints, but these b1 b2 bm that is written as in the constraint function, it is a part of the objective function when it comes to dual, that is minimization in this case, right? And while you write the coefficients in the that is primal problem, you have a coefficient matrix which is transposed to get the coefficient matrix of the dual, right? So from the primal problem, you can actually form your dual problem also. So in every linear programming problem, you have a primal problem, and corresponding to that primal problem, there is also a dual problem. I hope it's clear. Thank you, students.